Thank you for the introduction, and I should probably say thank you to my boss who couldn't make it to here, so that's why I'm here. And I will also jump straight into the acknowledgments because I'm very bad at doing this normally. So I'm basically giving Julien Michel's talk in the sense that he gave me the abstract and was like, here, write a talk about this. And I'm like, okay, I will do that. It was good that most of it is my work, so it's quite easy, but Jody Joris Jimenez, the guy here, and Stefano Basicio also contributed in what I'm talking about, basically. So just a brief overview. I know I only have 15 minutes, I'm trying to be quick, but I'm basically going to give you an idea of what our best practices are in the group, and if you have suggestions how to improve them, we're always welcome to hear them. And then I'm going to give an overview of our D3R challenge entry and our sample 5 challenge entry, and then I did a last minute change of the slides because we discussed reproducibility a lot yesterday, and we've actually run quite a few reproducibility calculations in the lab, so I thought I'll give you at least a brief introduction to what we've done there. Alright, so introductory slide. I guess the dream is we want to have a machine where we put a bunch of compounds in and a protein, we get a new drug out. Obviously, that's a bit ambitious. Okay, how about reliable free energy calculations so we can rank the compounds and tell a synthetic chemist go and create them in the lab. So the obligatory thermodynamic cycle slide here. What do we do in the Michel group? Well, we use chemical free energy calculations as our sort of overall awesome approach. And I thought since Julien was supposed to give the talk, I was slowly morphed into me. I'm very sorry about that. But so basically, as before, the idea is that we're going from compound circle to compound square by alchemically changing it with intermediates by having the switching function, which is governed by this lambda parameter. And in this way, we can then compute binding free energies or even hydration free energies, which I'm briefly talking about, in a much more effective way than trying to actually put a ligand and a protein in a box and see how that binds, because then we'll wait forever, basically. So it's all about automation and reproducibility. That's why this slide, essentially. So the idea is really we want to have an automated reproducible protocol which does not rely on Schrödinger's software, which we don't have, but sort of in the same vein that whenever we do something, we can go back and it's like, okay, so we picked this crystal structure and then did some docking and then we ran some calculations and we can easily rerun them again. So the way we do this at the moment is sort of this sort of semi-automated protocol, which basically involves we go from some smile strings and a PDB, then we do a lot of manual docking or hose inspections using things like Babel, Maestro. RDoc is one program we use. We also use Vina, whatever suits best, essentially. And then we do some mapping, as in if we have a big ligand library of, I don't know, 50 compounds, which isn't that big, I suppose, but we come up with the perturbation networks, i.e. what are the relative free energy calculations we actually want to do. At the moment, we still do this manually. We're looking into ways of automating this. There are some solutions out there, but the stuff I'm talking about at the moment was basically me sitting down doing the mapping. And then we run these alchemical free energy calculations, where in order to do automated setup of the small molecules, i.e. parameterization, and perturbation input files, essentially, we use something called Fxr setup, which Hannes Leffler was supposed to talk about, but I see he's not doing that anymore. And then for the actual simulations, we use Sire, OpenMM, or SOMD is the program called, which basically is a tool that wraps around OpenMM to allow us to run our free energy calculations. and that is sort of developed in-house. And same as all the analysis tools are also developed in-house, and we kind of do multiple replicates of the same simulation with different initial conditions. We use different ways of analyzing the data, try to compare them, and then we try and do a rigorous error analysis as well. So I'm going to go into a bit more detail on this here. So how do we actually calculate free energy? We have heard different ways, so there have been talks this morning talking about TI, people have mentioned bar, and people have mentioned mbar, so what we tend to use is mostly mbar, which is governed by this lovely looking equation here, where you essentially end up with a set of self-consistent equations you iterate, and then you estimate a free energy difference of, say, this guy versus this guy, where we've done a perturbation with, I don't know, 10 lambda intermediates of removing this group here to get to this guy. So one of the things we do is actually run estimates using thermodynamic integration and mbar from the same simulations we've run. So that means we can actually compare the free energy estimate. So this is an example for this perturbation, where I think it's this perturbation, where we get a difference in the free energies, which is somewhat significant. And mostly we actually look at simulations where the difference would be much smaller. And this is one way for us to check that hopefully the simulation we have is okay. Then another thing we look at in order to make sure we have, say, enough lambda windows is look at an overlap matrix in our perturbations. So basically the idea is, do we have enough contributions from neighboring replicas in order to have a valid mbar estimate? And basically, each time we run the simulation, we compute this overlap matrix, and then we go through a checklist of things do we have enough overlap? Is this a valid? Is this valid enough, or should we add more lambda windows? Should we do something else? And the other thing we do is the way we look at error estimates. So mbar comes, especially in the PyMbar implementation by Don Caldera, comes with errors on the free energy estimate, which is, as already discussed yesterday, is usually quite bad in the sense that it's a lower bound. So instead we usually run three repeats with different initial seeds of our simulations, and actually in this way then estimate errors. So to be a bit more precise about how we do this error estimate in this perturbation network, because as the previous speaker before the coffee break said, well, if we have we can run multiple we can run multiple ways. Sorry. I was too soon there. So basically, in order to get a good average of an error estimate, we run the same simulation 3 times. So we can run the perturbation from 7b to 7a, and from 7a to 7b from our initial parameterization. The backwards and the forwards should be identical, it shouldn't matter. In practice, the way we set up the simulations, we do get a difference, but in order to be sure that we don't have any weird conformational sampling problems, if the difference is small, then we're convinced, okay, we're probably okay with our free energy estimate here. Then we can average the numbers we get, so we get an average and the standard error on each of these edges, essentially. Then, as I said, we do many perturbations, so we don't just have a pair of two, but we can actually use a whole perturbation network that, in the smallest case, would be a cycle like this. So again, each edge, ideally, we do 3 repeats, and then also look at the cycle closure, which we basically do in the same way Schrödinger does it, but implemented by ourselves in a GitHub repository I maintain. So this is sort of the general workflow we do. We try and be as rigorous as possible with repeats and error estimates and so forth. And then we applied this to the D3R blinded dataset in 2015 and 2016. I'm only going to talk about the 2016 dataset. So D3R basically is a consortium in the US between academics and the pharma industry, where they identify data sets that might be interesting to predict binding affinities. So for the 2016 set, the target protein was Fxr, and the idea was to predict 36 crystallographic poses and rank 102 compounds and predict relative binding affinities for 2 subsets. Because in 2015 we weren't convinced that affinity ranking really works quite well with the methodologies we've had, and we don't want to really develop anything in that direction, we concentrated only on the relative binding affinity predictions for 2016. So you have set 1 and set 2. Set 1 has a scaffold that looks like this, and set 2 a scaffold that looks like this. So why is Fxr interesting or difficult? The binding site is actually very non-polar, but some of the ligands are charged. And especially in set 2, even from the crystal structures later released, multiple binding poses had to actually be considered, so that increases the number of computations needed. So here's an example for the perturbation map we used. So we have forwards and backwards calculations. I've only put repeats 3 times and different number of windows between 9 and 17 or something. And we did binding mode averaging using Boltzmann weights. In order to test our methodology, we did some literature scanning and sort of checked, does our way of doing free energy calculations give reasonably good results or not. So what we get is very bad mean unsigned errors, that's in kilojoules kcal per mole, but a passable correlation, at least for literature dataset 1, which comes from these 2 papers here. For literature dataset 2, the mean unsigned error was much better, but therefore the correlation was worse. But we kind of tested all the pitfalls we could have, and we're like, okay, probably we get a reasonable estimate on the blinded data set. So we did a bunch of different submissions, a full data set, then only the same charges, and an expert opinion where basically Julian looked at the data and wrote down a bunch of numbers. Luckily, mostly the expert opinion did worse than the others, but this is the full data set, and you can see there's a massive peak here, which is a massive overestimation. Guess what? That is the charged compound. So what we did was like, okay, maybe we can scale the charges and do like a poor man's attempt at a polarizable force field. Because we only had very little time, this didn't work out very well, don't do it. So stage 2 submission was after the release of the crystal structures, which meant for set 1, our crystal structure prediction or our binding pose was fine, so there was not much improvement. But for set 2, we actually didn't predict the pose well, so the RMSD was 2.7 angstrom. So with the release of the crystal structure, the second set of submissions was much better in the sense that we now had a better binding pose. And again, we had a full set, and then same charges scaled and all charges scaled in our sort of poor man's attempt by just, slowly changing the charges. So then for this we get an R value of 0.3 and a mean unsigned error of 1.41 at the first stage of set 2, where we had the wrong binding pose, and then for the second stage with a better binding pose, we actually can improve our correlation. And this is sort of the experimental versus computed. Now, all the data was released, and we can now compare our method to other methods, and in general compare how well we do in respect to other competitors. So let's look at set 1 first. So these error bars are computed by the D3R team, and they come from bootstrapping. That's why they're quite large. But in order to really be able to distinguish different methods, bootstrapping is a valid approach, and it basically shows that none of the methods are particularly better or worse than the other, particularly in the sort of top 5 or so. There's no good ranking there. Also, and none of them perform particularly well, so we have a Pearson R of 0.5. Our best submission is this one here, which is not significantly better or worse than the FEP Plus or AMBER or these MMPBSA methods. For set 2, this looks a bit different. 4 methods are significantly better than other methods. So identifying these is a mix of FEP Plus and Gromek's non-equilibrium pulling methods and a Monte Carlo method. But then we don't do that badly in comparison to other submissions. So what is a little bit worrying, some of the MMPBSA methods obviously are less computationally costly than the method we've used, which then is arguable maybe not the best to spend, I don't know, a month computing these numbers when you can do equally as well computing them for a day. In general, these data sets are too small to do a robust ranking. There are massive issues with changes in charges in relative free energy calculations, which was also discussed yesterday. And yeah, D3R is a great way to actually compare different methods, though, on blinded data sets. How much time do I have? 0. Shit. Okay. In that case, I will just like to skip ahead to this, just because we talked about reproducibility yesterday, and I will just give you one quick slide of solvation hydration free energies of basically this data with respect to this guy using Sarah OpenMM, Gromek's, and AMBER. And I'm just going to put that plot out here. So this is with respect to this guy. We have a difference in the mean unsigned error, essentially of 0.32 kcal between SOMD and AMBER and 0.27 kcal between SOMD and Gromek's. But the idea is that all the simulation parameters are actually identical, the analysis is identical, and this is what we get. We've done more computations than just this set, but I thought I'll just show that. And with that, I'll finish, and I'm sorry I've overrun.
Thank you very much.